I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, thank you for these students. We just ask that you bless our time together. Help us to glorify you, Lord, in what we do, Lord. In your name I pray. Amen. Okay, so I wanted to give you guys a little talk about how to do partial differentiation and how to find the linearization of a function. So let me get to it. So first of all, just a crash course on partial differentiation. So if you want me to give you a definition, I could. Should I give you a definition, though? Let me give you a definition, just to be safe. So if I have a function, all right, and it's a function from some subset of Rn, and let's suppose it's a real valued function, right? So this guy has Cartesian coordinates x1, x2, xn, for example. All right, typical choice. And so like we know, you can write a point x as x1, x2, xn, or if you wanted to, you could also write it how we could write it as a summation I equals 1 to n of x sub I ei, right? So we can write vectors as a sum of linear combinations of the standard basis. Usually we do E1, E2, E3, and here we're like in R3, or maybe we're in R2 or something, right? But we have this way of thinking about points as a sum of a linear combination of the standard basis, right? So with this technology in hand, it's pretty easy to define the partial derivative. In particular, partial f, partial xi, all right? What it is I guess I could give it to you in terms of a limit, but I think I'm going to give it to you instead like this. It's ddt of f. Oh, and I need to tell you at what point. So suppose this is being done at the point P, all right? So it's ddt of f of P plus t times ei. And I put t equal to 0 at the end of it. I'm regretting writing this. I don't think it helps us. Let me just show you what this looks like at n equals 2 partial f partial x at the point x naught comma y naught. Looks like the limit, as now I'm regretting writing this, f of x naught plus h comma y naught minus f of x naught y naught, all divided by h. So this is the partial derivative of f with respect to x. So I mean, you can kind of see what's going on in this definition. You see what's happening to the y variable. The y variable is fixed at y naught. It doesn't change in the difference, right? So we're really just studying the change in the difference, the change in the first variable, right? So, I mean, this is equal to ddt of f of x naught y naught plus t times. Oh, well, let me just shut up. This is not helping you. Let me just get to the point. Let me show you examples. This is hopeless. I can't explain that much detail here. Example 1. Partial x of x squared y plus x plus y. There we go. So the reason that we use partial instead of d is because there's several variables, right? Okay, so basically the way it works is you just differentiate x like normal, and you can pull the y out. So this is just like a constant. So this y just differentiates to 0. And what do you think partial x is? What do you think the partial derivative of x squared is with respect to x? Right, we got 2xy plus 1. Now, I know most of you have had Calc 3, right? So I'm completely boring you at the moment. But there are 2 people in here who have not had Calc 3, is that right? Am I talking to 2 people? Hey, you're in my Calc 3. No, behind you. It's a...
I haven't taken it, but I just had them explaining my physics 2 class. So.
Oh, okay. Yeah, I mean, you really can't do physics without Calculus 3, honestly. Just a few more examples so we get the sense of it. Example 2. If I was going to take the partial derivative with respect to y of e to the x squared times y. So there's a chain rule. So we do e to the x squared y because that's the outside function. And then I do partial y of the inside function. Right? But with respect to the y derivative is done holding x fixed. X is like a constant for partial derivative with respect to y. So basically we just take this and move it over here, right? And what's partial y? It's 1, right? So this just gives me x squared e to the x squared y. Let's see here. What if we were going to differentiate with respect to z a vector of things? X squared plus z, comma, e to the z squared plus x. And let's see here. How about x, y, z squared? So you're like, I don't know how to partially differentiate a vector of things. Yes, you do. In Calculus 3, you calculate these things, remember? Remember xu, xv, this gives you the normal vector of the parameterization by u and v. You take the cross product of the partial derivatives of the parameterization. Cross product of that gives you the normal vector to the surface. This is how we set up the surface integral at the very end of the course. You weren't tested on it. You weren't tested on it. You weren't tested on it. Sorry, there's fighting words for me. But the point is that is actually a partial derivative of a vector. This is xu, yu, zu, if I'm talking about x being x, y, z. Here, both x, y, and z are all functions of u and v. This gives us a parameterization of a surface, right? So my point, all I'm trying to say, guys, is you've already calculated this kind of partial derivative back here. You just may not have thought of it that way. And the way you partially differentiate a vector is just component-wise. So this would give me 1. This gives me 2z e to the z squared. And differentiating that gives me 2xyz. Do I need to do more, or do you guys understand? I think you, any questions? Should I do more? Let me go on to the linear algebra part of it then. So, in Calculus 3, many of you have had it, right? You were taught about the tangent plane to a function of 2 variables, right? So you do something like, here's a graph. I think Dr. Smith might have talked about this a little bit last time. But you've got something like x, y, z. This thing is z equals to f of x comma y, right? And you pick a point, right? And so we can visualize the this down here is the domain of f. We can view it that way, right? For a function of 2 variables. So the graph of f is the set of x, y, z such that z is equal to f of x, y, where x and y are in the domain of f, right? This is the graph of a function of 2 variables. And of course, that's generally curvy. But you learned, right, that you can look at the tangent plane to this thing here like that, right? The set of all tangent vectors through that point. And perhaps you learned that that graph, that tangent plane, right, which lifts off the curved surface of the graph, is exactly the graph of the linearization of the function. All right, just like the tangent line is the graph of a linearization of a function of one variable. So the linearization of f, all right, at this point, I need to give this point a name. Let's call it p, right? Well, maybe I should call it x naught, y naught. So at that point, wow, this is awful notation. So the linearization of f at the point x naught, y naught, all right, that as a function of x and y is what? It's equal to the function at x naught comma y naught, right, plus another two pieces, right? The other two pieces we build from the partial derivatives. In particular, you do plus f sub x, which is the partial derivative of x with respect to x at the point, times x minus x naught, plus f sub y at the point, times y minus y naught. So this collectively is exactly the gradient of f, right, at the point x naught, y naught, dotted with the change vector x minus x naught, y minus y naught. Right? That graph of this thing, if you set this equal to z, right, set all of this equal to z, it gives you the tangent plane, supposing it exists. And that gives you a very good approximation for z close to the point of approximation, right? So let's see here. The question then is, how do we generalize this, right? How does this work for functions of more variables? Like, what if instead of having a function from R2 to R, what if I have something like a function from R, Rn to Rm? Right, so the question is, how does this generalize? Oh, something I should tell you guys. Do you guys know what's if you don't want the linearization, suppose you want the best quadratic approximation? You do f at the point P plus the gradient of f at the point P dotted with r minus P, right? So this stuff here is f of P. Maybe I should put a sub naught on it to feel better about my life. There we go. Now I feel more consistent in my notation. So these two pieces, the linearization, yowzers. This piece right here, right? These are the same. What's next? You may not have been taught this, but here's interesting. What comes after this is the following. You have what's called the Hessian, Q at the point P naught, right? And actually, this is also, you can write it in terms of R minus P naught, like that. Just to give you a specific, what this looks like in a specific case, in n equals 2, which I guess is what I'm doing, so why not 1/2 fxx at the point P naught times the delta x squared plus fxy at the point P naught delta x delta y plus 1/2 fyy at the point P naught times delta y squared, where of course I'm using delta x is equal to x minus x naught and delta y is y minus y naught. So like the next term up here is this thing. This is the Q, the so-called Hessian. This will be interesting. We'll come back to this later in the course. That's why I'm telling you now, because just to get it out there. Like later we'll come back to this and we'll study how to rip apart the Hessian using eigenvectors. We can write this as a matrix, in fact. This can be rewritten as a matrix. You can write it as fxx, fxy, fxy, fyy. And on this side, you can do delta x, delta y as a column. And on the other side, you can multiply by delta x, delta y as a row. And this will get you this formula up here. So in fact, you can see a matrix in the second order piece as well. This is what's called a quadratic form. We study this later. But as long as I've come this far, I should mention this. Okay, so let me get back to our main order of business, which is how do we linearize a function of more variables? It's going to be somewhat anticlimactic. What I'm about to tell you is really, really simple. So I hope you won't be too disappointed. So, task, linearize a function, let's say big F, from some subset. So it's got some domain. It's a subset of Rm, right? M or N? N, right? N, yeah. And I'm saying its output is M. So this would be what's called an M-valued, well, an RM-valued function of Rn. That's what the thing we're working on right now is. In this terminology, my previous thing we're studying over here is an R-valued function of R2, right? Okay, so getting to it. The linearization of F, right, at a point P, what it's going to be is simply this. Supposing the partial derivatives exist, all right? What we do is, oh, sorry. So I should feed it, let's say I need a variable. Oh, how about x? This is a vector. I'll use a vector on it to emphasize it's a vector. X vector is equal to, I'm sorry guys, just to avoid confusion with the scalar x, which we often use, I'll use an R vector just to make sure we're not thinking of it as the scalar variable x, all right? So the linearization at the point R is given to be, we take the function, the mapping rather, f, we evaluate it at the point P, all right? Then plus what's called the derivative, f prime of P, all right, times R minus P. Yep, that is it. Now the question, of course, the devil's in the detail here is, here f prime of P is also defined to be the Jacobian of f at P. All right, the so-called Jacobian of f at P. Let me be more specific. How do you calculate that? So one way you can calculate that is partial f, partial x1 at the point P, and then partial f, partial x2 at the point P. Sorry, this at the point P stuff drags me down. Partial f, partial xn at the point P. Okay, enough of this at the point P stuff. Let me just divorce myself of the point for a second here, if you don't mind a pointless comment. Sorry. It amuses me more than it should. So dropping the explicit point dependence. This is the Jacobian. It is an m by n matrix. Keep in mind that this f here, right, is actually equal to a column of functions. It's f1, it's f2. It's all the way down to how many? It's m valued, right? These are the so-called m component functions of f. So it's got these m component functions like that. And so there's a different way you could look at this Jacobian, which is useful to make contact with what we did over there. The other way you could look at it, instead of being column by column, you could look at it by row, right? If you look at this row by row, what you have is a stack. First of all, you've got gradient of the first component function, gradient of the second component function, and so forth and so on, gradient of the mth component function. So like this thing right here is, you could look at it as the gradient of f, right? Or you could look at it as a row vector, partial f, partial x, partial f, partial y, multiplied by that. Right? You could look at it either way. In fact, I have both formulas here. This versus that. Now, in terms of calculating, I don't like the stack of gradients as much. For me, this is way, way easier to calculate. Let me show you. So if we have, say, f of x comma y, comma z, equal to x squared plus y squared, and then y squared plus z squared, just to keep it simple, let's calculate the Jacobian of f. The Jacobian of f is equal to, what is it? Well, we've got three things, right? So we've got partial f, partial x, partial f, partial y, partial f, partial z. It should be a what? 2 by 3, right? 2 rows, 3 columns. Keep in mind my sneaky notation, right? Yeah.
Just so you know, we did this last class.
All of it?
We calculated Jacobians and then plugged in different points, and we guessed. We also used the formula where we guessed to get closer and closer to this.
Oh, good. I will not go that far. I'm going to reinforce the Jacobian part, but that's as far as I go.
Okay.
So the confusing part that what you actually need to see more about, I won't talk about. But this part, I think, is reasonable for a test, is my point. Yeah. The other part is very numerical and would be hard for me to work into an in-class test, but is interesting. Yeah, of course. So this is actually x squared plus y squared. So yeah, I'm sorry if there's, and I do very much appreciate that comment, if there's overlap here. So I'll try to keep it brief. So anyway, this Jacobian would be what? It would be, we got 2x, that's a 2. 2x, 0, partial derivative with respect to y. We've got 2y, 2y, and then with respect to z, I got 0, I've got 2z. There you go. Now suppose you actually wanted to find the best approximation for this function. Let's say approximate f at 1, 2, 3. Right? So then I could say that f of x, y, z is approximately, well, it's approximately 1 plus 4, 1 squared plus 2 squared, comma, 2 squared plus 3 squared. Right, this is my f of 1, 2, 3. And then plus, I'm supposed to do, what's the Jacobian of f at 1, 2, 3? 2, 0, 4, 4. I'm plugging in 1, 2, and 3 into here, okay? X equal to 1, y equals to 2, z equals to 3. 0, 6, okay. And let's see here, then times my x minus 1, y minus 2, z minus 3 vector. Change vector, really, right? And so just to complete the story here, this would be equal to, what would it be? Multiply this out, right? That's 5 plus 2 times 2 times x minus 1 plus 4 times y minus 2. There's no z term, comma. 4 plus 9 is 13 plus 4 times y minus 2. And I won't even multiply this out. I'll just leave it like this. Plus 6 times z minus 3. And so there you go. This thing right here is the best linear approximation to this nonlinear function at the point 1, 2, 3. If you stay close to 1, 2, 3, this is a very good approximation to the function. There are theorems of advanced calculus which quantify precisely how good an approximation it is if you want to get into it. These things are known. Anyway, I just thought I thought I should go through this again just in case, because I didn't know how sketchy what Dr. Smith was doing last time was, if it was enough for you guys to understand this or not. Like, I'm going to put a question on your mission, which is like this, so you have a chance to work one out for yourself, you know. Does that seem fair? Okay. And of course, for me, the joy in this discussion is the ubiquity of this linearization idea. This same linearization gives you the tangent line in Calculus 1, the tangent line to curves in Calculus 3, the tangent plane in Calculus 3, really the mathematics behind surface integrals. Like everything you've done differentiation-wise in calculus, it somehow or another fits into this thing. Totally general. And the chain rule, like the chain rule for functions of several variables can be viewed as, all those things can be viewed as multiplication of Jacobian matrices, for example. All of those weird chain rules you saw in Calculus 3, they're all multiplication of Jacobian matrices. Anyway, I digress. And with that, I will move on to our next topic. Hey, I actually did that in about 30 minutes. I thought I had planned to do it in 30 minutes, and I thought what would end up happening is it would end up being an hour, and then I would regret my life. So I think that gives us a good time to look at my kid. So let's do that. What's that? Yeah, I mean, that's it for this part of it, but we still have more to cover today. Hey, so offensive. Are you, yeah, was that about my kid or about my teaching? Like, you lose either way.
Yes.
You're just like, it's been a long day. I want to go home. I know, I hear you. Trust me, I do.
So what's your kid's name?
Benjamin. Yes,
Have you slept yet?
yeah, I have slept pretty well. Jenny, not so much. I'm a bad husband. Let's see here. Let's see here. Where is it? Somewhere in here I've got the picture. Oh, there it is.
Oh.
Yeah, it's a baby. Let's see here. There you go. Yeah, that's more or less how most of my children look at this age, give or take. In fact, like pretty much how all babies look at this age. But I don't know. Daniel looked different, you know, because he has more Chinese features. But this guy will probably look like my other son, Matthew, I think, a lot when he's a little bit older. All of a sudden, Matthew looks huge. Like, Matthew was a little guy, and then all of a sudden, he's huge. And like, Matthew's like fascinated looking at Benjamin's fingers and stuff. He's like, baby, small. Like, yeah. And then people will be like, you're big. And he'll be like, no, daddy big. Like, hey. So anyway, my children.
Do you have like a family picture?
Not very fresh.
Which ones came in here with us?
I actually need to update this. Let's see here. Here are many family pictures, but that one's pretty good as they go. This one, where's my laser? Where did I put my laser? laser. My laser. Where's my laser? Oh, here it is. Yeah, so of course Benjamin's not pictured because this is last time. I think this is the last time we went to Disney World. So here's Hannah. This is Isaac. Daniel, my Chinese son, and this is Matthew, who is now bigger. He's not quite as big as Isaac is here, but Isaac is nearly 6. He'll be 6 very soon. I think his birthday is in 2 days now. It's very exciting. And Daniel is 8, soon to be 9. Hannah is 10, soon to be 11. So yeah.
So you give him the rest of his $9 to buy stuff?
Oh yeah. You talking about Isaac and his? He just ruined that day fussing about that stupid Flama. So finally, a couple days later, he got the money to get the thing, right? He gets it, and then doesn't play with it. And it's just, he's just.
You can reuse it.
I know he's got this he gets obsessed with a particular toy, and it's really annoying. So we're trying to correct that while he's young, so he doesn't get older. Maybe you have friends like this. I don't know. Maybe you are like this. Hopefully not, right? When your happiness is based on something you don't control, it's a bad way to live, right? Well, I guess that's not entirely true either. As Christians, of course, there's lots we don't control, but let's say you should let your happiness depend on something that is more reliable than your ability to secure monetary funds to buy plastic pieces of junk from China. I'm sorry, not China. From, where is it? Legos. So, where is Legos from? I forget. Is it Netherlands or? I forget. Connecticut? Yes, Isaac is the funny one. I'm supposed to do math with you guys. I'm sorry. What am I doing? I'm sorry. I'm supposed to do math here. You guys are a bad influence on me. Let's see here. Hey, I said go away. Go away. All right, so our next topic, which I think you guys will enjoy, is determinants. Now, so for the, there have been some applications that I haven't worked into class yet. So whatever I couldn't work into class so far, I'll try to work into your homework, which will be due. And did I post the course planner yet in here?
Yes.
Yes. Okay, so I think on there I say when mission 1 is due. Do you remember when it was?
I think 23rd.
You're like, quiz 2 is due today. That's enough trouble. Enough trouble for one day. I'm not looking for another trouble another day. What's that?
I think the 23rd.
The 23rd? Okay. So I'm hoping to get that mission posted for you guys sometime pretty soon. Ideally tonight. I've started working on it. I just haven't fleshed it out entirely yet. But I'm going to try to make the problems on that mission interesting. So they'll actually be applied problems, some of them, right? So maybe some things like the discrete dynamical problem. Do you guys know what that is?
The Markov chain.
The Markov chain thing? So the Markov chain thing, basically you have some state vector. And so the state vector, something like, it might be like x, xi, yi is equal to your vector, right? And then you have some transition matrix. Which you can call it whatever you want, M, right? And then the deal is the I plus 1th state vector is given by M times the ith one. So you start out with an initial state, right? So your initial state would be something like, we'd call it R naught, right? Then to find R1, you do M times R naught, right? And then to find R2, you do M times R1. But what is M times R1? I'm really regretting putting a vector symbol on this R. This is applied linear algebra. We don't want to have to put vectors on vectors, right? If it's okay with you guys, I'm tired of vectoring things. It's just R. No vectors. No vectors. Too many vectors in my life.
M squared R0.
M squared R0, right. And having done this once, you can do it k-fold times, right? So like, or let's say n-fold times. Rn, the nth state vector, would be the nth power of m times r naught. So if you can calculate the nth power of a matrix, you can figure out where this system goes to. Right? So the way this works is something like, let's say x, xi could equal the number of cats, and y sub I could equal the number of dogs. All right, and we could let m equal to, I don't know, 0.3, 0.7, 0.2, 0. Can I do that? 8. I don't know if I can do this or not. We'll decide in a second if it makes sense or not. And so if I say that R naught is equal to, I don't know, 100, what's R1? Hey, I'm supposed to be talking about determinants. Why do you guys let me do this? It's all my fault. Anyway. I don't know. It was for a good cause. Can you guys multiply that? All right, so you got, so what do we get here? So you got 50 and what? And 150. All right. So this is a somewhat, I mean, this would require genetic engineering, my example. So what we're looking at is the number of cats, the number of dogs. This transition matrix, what it says is that as the state evolves, I start with 100 dogs and 100 cats, rather, 100 dogs. And then the state machine, whatever it is, causes 50 of those dogs to become cats. So this probably would make more sense if you, instead of said cats and dogs, you could do something like number of healthy people, number of sick people. Now this would be the spread of, this would be, so this would be, let's see here, this means, so what does this say? It says 30% of the healthy people stay healthy, and how does this work? I'm sorry, I'm having trouble thinking. So I think the interpretation here, 30% of healthy people stay healthy, 70% of healthy people get sick. Ooh, this is bad. Maybe let's make this more interesting. Sick people, right? Healthy people. I think now the setup starts to make more sense, right? Because let's be optimistic, right? So you got, this says that 30% of the sick people stay sick, whereas 70% of them get healthy. And this over here says that 20% of the healthy people get sick, whereas 80% of them stay healthy. So as you can see what happened, we started with 100 sick people, 100 healthy people, and then we get 50 sick people and 150 healthy people. Right? So supposing there's some, rates of disease communication that cause this to happen, we're assuming that people don't die, right? So you could make more interesting systems where people are allowed to die and so forth. Your book has a little bit more variation, but this is basically a Markov chain, and you keep going, and you can study what happens. So I'll try to have a homework problem that's based on this kind of example. It's fun because it gives us an application for powers of a matrix, which you might not have expected. Yeah. There's also that example about adjacency in graphs, which is really interesting.
So which matrix would I raise the power of, or raise n to a certain power to figure out what my R of 3 is? Or
right, so yeah, if I keep going, I just just find the m to an arbitrary power will give me the state vector. Now, what would be like a stable point to, if you could imagine, keep going on and on and on, eventually you reach some stable equilibrium, right? What you 0 to 100? Is that it?
Well, I'm guessing there's a total of 200 people in the system.
Well, but it could be that if you keep going down, it might like bump back up. Like it could be if this number gets big enough, that one starts getting. There could be some kind of balancing act. I'd have to do further. Hey, I think we just found a Homer problem.
Oh, okay. Where does it
So,
stop?
yeah, that's the question: is what happens with this as we go to infinity? I'll make this one of your problems. Okay. Again, this question is elegantly and beautifully answered by what's called an eigenvector later. This question ultimately brings us back to the concept of an eigenvector. But that's a little bit later in the course, but I'm just saying we'll get back to it. All right, so let me talk to you guys about determinants. What is a determinant? Why do we care? And what good are they? So here's a slogan that's pretty good. Determinants are volume. I'll show you what I mean. So example 1, if I take the determinant of A, B, C, D, by definition, this is AD minus BC. So this is definition of a 2 by 2 determinant. So the determinant is going to be a particular number that we get from a square matrix. We can only take the determinant of a square matrix, and the significance of that number is it's going to represent the volume, which is subtended by the parallel, the n piped, which would be formed by taking the columns of the matrix and making it into like an n volume. So just to give you a stupid example, if we look at the determinant of 1, 0, 0, 3, what is this? This is a rectangle. So like here's x, like that, and like that, right? So this gives me this actually just plain old rectangle. What's the area of that? 3, right. Now, the significance of the sign, if you look at the determinant of 3, 0, 3, 1, 0, what's that equal to? By my definition above, that's minus 3. And what's the difference there? Why is this minus 3 and why is that 3? I said it's volume. That's a slogan. That means it's a lie, right? It's part of marketing. It's fundamentally dishonest, right? The exact opposite of math is marketing, I think. I'm sorry. I hate marketing so very, very much. I mean, when people come to my house to try to sell me something, they just don't even know how much of their time they're wasting. If you want me to buy something, set a website up and let me investigate it. When I want to buy it, I will buy it, not before then. Not because of a conversation I have with you. I don't care if you care about my children and my lovely house, blah, 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 blah. No, I don't want any of these conversations. Thank you. Sorry, I digress. So the point of this is the 1, 0 vector and the 0, 3 vector, their relation is that you're looking at a counterclockwise rotation of 1, 0 to 0, 3, right? This one, if you think of this as the first thing and that is the second thing, you see what we're doing is to get from here to here, I have to do a clockwise rotation. And that's the reason for the minus. If the second vector is obtained from the first by a counterclockwise rotation, again, if the second vector is obtained from the first by a counterclockwise rotation, positive determinant. If the second vector is obtained from the first by a clockwise rotation, it's negative. So in this sense, the sign of the determinant determines the orientation of the vectors with respect to each other. This is the geometric meaning of it. What does it mean if there's 0? If this is equal to 0, what do you get? If AD minus BC is equal to 0, what does that tell you? And so let's suppose that AD minus BC is not equal to 0, and let's suppose that D is not equal to 0. What's that say about A? A is equal to BC over D, right? So what's that say about A comma C? It's equal to what? It's equal to BC over D comma C, right? Which is C times what? Times B over D times 1, right? Which is also C over D times B comma D. What does that say? That says AC, this one, is a scalar multiple of the other one. In other words, they're collinear. And you can prove that if D is not equal to, well, I just assumed D was not equal to 0, right? So, fine, yeah. But you could do for other cases as well. In short, if the determinant is 0, that means that the vectors are not independent. They're like collinear, okay? And that the volume, quote unquote volume, I say volume, I should put quotes on that because I'm using volume in the generalized sense, all right? Now, another thing we would notice is A, B, C, D. What was that inverse? It was, remember, AD minus BC, D minus B minus C, A, right? What is this? This is the determinant of the matrix, right? So, by the way, comment. A inverse exists must imply that the determinant of A is not equal to 0. Now I have better ways of proving that for you, all right? Let me just tell you a fun fact. Here's a way to prove that. And I say fun fact because this actually takes me the better part of about 20 or 30 minutes in the 321 class to derive. This is not at all an easy thing to prove. But it is true, in fact, that the determinant of a product is the product of the determinants. So think about invertibility of a matrix. If A is invertible, what's that mean? That means A times A inverse is equal to what? I. Oh, other fun fact? The determinant of the identity matrix, n by n identity matrix, is just 1. This basically defines the volume of the unit hypercube to be 1, if you want to think of it that way. But the determinant is defined to make that happen. That's part of the bedrock of the determinant, is to make the determinant of the identity matrix 1. Okay? Anyway, it's true. So what happens when you calculate the determinant of this equation? What do we get? So what's this say? The determinant of the inverse matrix is what? So this is the relation between the matrix, the determinant of the inverse, versus the determinant of the matrix, provided the inverse exists, right? You notice that if the inverse doesn't exist, what does the determinant of A have to be? I mean, I'm being a little bit illogical here. Certainly, if the inverse exists, then this equation shows that the determinant cannot be 0. If the determinant was 0, that would spoil this equation for sure, right? The reverse implication showing that the determinant is 0 forces the inverse not to exist. That's a little bit more subtle. That's the thing I'll show in 321, but it doesn't really matter to us here. It's just a fun fact for you. This is another way to test if the matrix is invertible, right? You can check this. If the determinant is non-zero, the matrix is invertible, which means you can go on your merry way and do that row reduction with the super augmented matrix, and you can calculate the inverse if you want. All right? So that's nice. You're like, okay, are there any other properties of determinants you should know about? Well, yeah, there's a few. The other big one that comes to mind right offhand is the determinant of the transpose is the determinant of the matrix, like that. This is a property of determinants. It's invariant under transposition. If you think about, I said they're volume, so they're like the volume of the columns thought of as the edges to something. So if you change that to say it's the volume of the rows thought of something, should it matter whether you write your columns as rows or as, I mean, if you write the edges of the shape as columns or as rows, should it change the formula for the determinant? No, it shouldn't, right? So like it's totally unsurprising from a geometric perspective that this identity holds true for the determinant, but it does. Again, to actually prove that. So, I said you can calculate the determinant for an n by n matrix, right? I just showed you 2 by 2. How do we do 3 by 3? So here we go. I'll show you the definition by cofactors. So we'll do A, B, C, D, E, F, G, H, I, for lack of imagination. And this we can define a couple different ways. This right here is the top row. So I'm going to do what's called the expansion by cofactors on the top row. So this is usually kind of the typical pattern. You guys have had calculus 3. This is the same pattern you use to calculate the cross product. For those of you who've had calculus 3, sorry. But for those of you who haven't, it's not really a big deal. So we do A times the determinant. My E is getting too tall. Determinant of E, F, H, I minus B times the determinant of DFGI plus C times the determinant of DEGH, where those 2 by 2 determinants we already defined. And so let's see here, just to give you a sense of how this works. Expansion by cofactors, you could also go other ways. Like, so the signs here go like this, plus, minus, plus, minus, plus, minus, plus, minus, plus, so to speak, all right? So these are the signs, the signs for the cofactors, cofactor expansion. So let me just show you another one just to make sure we have, this maybe you haven't seen before. How would you expand on the middle row here, middle column? To expand on that, it would look like this. B, and then I do the determinant of everything that's not in the B row and column. So that's D, F, G, I. And I am already wrong because I haven't followed my sign chart, right? I'm starting with B. It gets a minus. Just like B up here got a minus. All right, and then plus E times the determinant of ACGI. And then plus 8, minus rather, H, times the determinant of, and by the way, if you don't like my notation, if you want to use this for determinant, I'm cool with that. I just write determinant because I don't like this and this to be so different in meaning. That's just, I can't use this for determinant. It's just, it bothers me. The danger for confusion for me is too great there. I can't do it. So I write determinant. It's not a lot to write. H, so I got A, C, D, F. Again, this is what's called Laplace's expansion by minors. You got many choices, right? You can expand on row 1, row 2, row 3, column 1, column 2, column 3. There's six possible expansions by minor. Yep.
So the
Well,
each one of the parts and then break
that-
it down into its square?
That's how I'm showing you how to calculate it, but to be, I mean,
There's a better way, obviously, but
Yes.
in this case, it's recursive.
right, the way to calculate for numerical examples is recursive. The real definition, I'm fighting myself. I'm not going to write it. I'm not going to write it. I'll show you in the projector in a minute. But another example. What example am I on? Example. Oh, my examples restarted. I reset the counter. So this is example 2. So determinant of 1, 2, 3, 4, 4, 4, 0, 1, 1. See how that goes? So I'm just going to write it down. That's 1 times 4 minus 4, minus 2 times 4 minus 0, plus 3 times 4 minus 0. I did the expansion across the top row. So it looks to me like that's... You shouldn't try to copy down my work. You should try to work it out for yourself, okay? In this case, what do we get? I get 0, minus 8, plus 12. I think I got 4. Let me show you, there's a trick. Now, I should warn you, this is a trick for the 3 by 3 case. It does not work for the 4 by 4 case. I had some student try that on my 321 test, and well, I'm sorry, but it's not available. So this technology is n equals 3 exclusive. So what you do is you take your matrix that you want to calculate the determinant of, and then you write it again, but not the whole thing, just the first 2 columns. All right. And so the way it works is you do like this, and like this, and like this. That gives me 1 times 4 times 1, plus 2 times 4 times 0, plus 3 times 4 times 1. Pluses on these, wait a minute. Are those the minuses?
Those are the pluses.
Those are the pluses, okay. I mean, this is some stupid trick, so like, there's always, this is the danger of me with tricks, is like I don't really believe in them, so I don't remember them. But this helps people, so I'm showing you. This one, this one, and you gotta be careful with that. Those are subtractions. Minus 0 times 4 times 3, minus 1 times 4 times 1, minus 1 times 4 times 2. Which is what? Oh, this 4 cancels with that 4. That's just 0. So we get 12 minus 4.
No, it's
12
12.
minus 8.
12 minus, oh, gosh. It is what it is. Okay, so as I said, I'm going to make a lot of errors in here. It's unavoidable.
Would this work for any other square?
No, as I was saying at the start of this, no can do so.
Not even 6 times 6 and then 2 blocks?
All right, let me show you why this, you did it. This is your question's fault. But so the definition is that the determinant of A is the sum I1 in of epsilon I1, I2, in A, I11 A, I22, and so forth. AINN. Now this thing is 1 if the indices are all in order from 1 to n, and anytime you flip 2 of them, you get a minus.